Space, the final frontier. These are the episodes of Sun Like It Hot. Its 3-year mission to explore strange new physics, to seek out new solar topics and new audiences, to boldly go where no YouTube series has gone before. Welcome to the first episode of Sun Like It Hot. My name is Mark Kornbluth, and this is a show about the sun. For this series, I'm going to be your guide to the happenings of the solar system. Think of me as Virgil, and you are Dante. We are about to start exploring the inferno that is the region around the sun. This region, called the heliosphere, encompasses all the space that surrounds the solar system and permeates it, and its boundary is a super strong magnetic field of the sun that separates us from interstellar space. For those curious, the term heliosphere is derived from the Greek god of the sun, Helios. In Greek mythology, every day Helios would drive his chariot across the sky, and this deity-chariot duo was actually the personification of the sun. So we get the word helio to describe things related to the sun because of the Greek origins. For the other half of heliosphere, this is actually a misrepresentation of what the heliosphere actually looks like. Counter to what you might think, the heliosphere is not actually a sphere. Crazy, right? No, this isn't just one of those times astronomers are trying to mess with people. Over time, our concept of the heliosphere has evolved quite a bit. We have been able to get a better grasp of what the heliosphere actually is with better technology, and the currently accepted shape of the heliosphere is a hemisphere on one side and a comet-like tail on the other, caused by the sun traveling around the galaxy. A new theory out there has actually suggested that this comet-like model is wrong, and that instead the heliosphere has two jets. But hey, that is a topic for another day. What I want to talk about today is how we got here. There's a lot to talk about when discussing the sun, but no explanation would be complete without telling you how the sun got here in the first place. So where should I begin? How about the beginning of all beginnings? The biggest bang that never actually boomed. Yeah, let's start with the Big Bang. So how did it all start? Well, that is a question that has puzzled scientists for quite some time. I wish I could tell you the intricate details of how it all actually happened, but if I could, I'd likely be writing my Nobel Prize speech too. What the leading theories suggest are that, in the beginning, everything you know and love was squeezed into the tiniest imaginable space known as a singularity. This singularity was so dense that all of the fundamental forces that cause the universe to work were all squished together to the point you couldn't tell them apart. Imagine gravity acting the same way as magnets or electric charges. Don't worry, I can't really imagine it either. But anyway, all of the fundamental forces, the gravitational force, the strong force, the weak force, and the electromagnetic force, were all squeezed together in such a tight space that they were essentially the same force. Now, I for one wouldn't want to be in that super cozy space for too long, and gravity felt the same way. Eventually, gravity was like, hey, I don't need this anymore. I'm going to force my way out of here. See what I did there? And it left the joint. The strong force, which is the force that keeps protons and neutrons together in the center of atoms, saw gravity leave and was like, that gravity may have been onto something. Why should I be all cramped up with the weak and electromagnetic forces when I can have all the space in the universe? Well, with those two forces leaving, the electromagnetic and weak forces started freaking out. Imagine the universe's biggest temper tantrum. Actually, the universe is the physical manifestation of the temper tantrum. But the thing is, the Big Bang wasn't a bang at all. The Big Bang was the creation of the universe. For there to be a bang, there needs to be something to bang into. Sound doesn't travel through nothing, and, well, since the Big Bang was everything, the Big Whimper may be a more accurate way to describe it. Though there wasn't really a whimper either. Anyway, shortly after the creation of the universe, everything went through a period of inflation. You think inflation of money is bad? Try expanding by a factor of 10 to the 50th power. That's a 1 followed by 50 zeros in a matter of 10 to the minus 32 seconds. That's a decimal point followed by 31 zeros before the 1. This was a crazy quick and gigantic expansion, and you can actually see the result of this inflation in what is known as the cosmic microwave background radiation, which is light at the microwave wavelength which permeates the entire universe. It was actually accidentally discovered by Arno Penzias and Robert Woodrow Wilson in 1964, and their accidental discovery won them the Nobel Prize. So remember, kids, you could be one accident away from a Nobel Prize! Anyway, where was I? Oh, right. So we had some crazy inflation, and about 380,000 years after the Big Bang, the universe was finally cooled down enough that the electrons and protons could come together and form hydrogen. So what happens when you have hydrogen? You can form stars. Now, most of the hydrogen in the universe will not be involved in the star formation process. Some of it will, though, when you have that pesky gravitational force bringing a lot of it together in a really tight, dense space. This volume can get really hot, And when it's hot enough, you can get hydrogen atoms coming together in a process called fusion that creates helium. With this, we have our first stars. Remember, I only said electrons and protons came together to form hydrogen. The early universe was hot enough that you also had hydrogen fusing into helium before stars, but in small amounts. You need stellar fusion to get heavier elements than that. So the first stars in the universe only had hydrogen and a wee bit of helium. From these first stars, the heavier metals that we know and love, like carbon, were formed. When these first stars would die, they would essentially explode and eject all of their material. From this ejected stardust, other stars could then form. And you guessed it, our sun included. Our sun formed out of stardust, and when it was just a baby star, it was surrounded by a disk of gas and dust that also came from dead stars. In this disk, pockets of the gas and dust came together to form the planets, asteroids, and comets of our solar system. So our sun is made from stars, our planet is made from stars, and we are made from stars. Cool, right? Anyway, there is still a lot to learn about the stars, but the best way to do it is to study the sun. The best way to study something is to observe it. So what better way to study stars and how they work than by studying our own personal star? That's what I do in grad school. And with this series, I plan to teach you about stars through the lens of our very own sun. I'll teach you about the structure of the sun, the stuff being ejected from the sun known as the solar wind, and the really big bursts known as coronal mass ejections. I'll tell you why we have aurora on Earth, and how the sun is connected to the very technology we use here. I'll show you what is going on at the very edge of the solar system, and you will get to be my special guest as I work with my research group to figure out what the heliosphere actually looks like. We have a fun journey ahead of us, and I hope you will join me on this exciting ride through the solar system and beyond. Thanks for the view.